Hi, students. Today I would like to lecture on Chapter 7. It's really an introduction to reactions and aqueous solutions. Okay, we're going to start off today by talking about some general things about aqueous solutions, what makes them interesting and important. You probably know that we do a lot of our reactions in aqueous solution, and there's a lot of reasons for that. And I want to make sure that we talk about those things, those general things, before we do anything else. We're going to talk a little bit about predicting reactions, what things can predict whether a reaction happens. Sometimes we call these things driving forces. It's kind of a general fuzzy term that we use, but it gets the point across, like something drives the reaction forward, something makes the reaction happen. And then we'll start talking about specific kinds of reactions. So let's talk about predictions or driving forces, right? So in other words, what makes a reaction happen? Later on, when you learn some basic thermodynamics, we'll have different words for this, some more specific words like spontaneity, entropy, free energy. But for now, we're just going to talk about kind of in general terms. There's many things that can kind of make a reaction happen or tell you that a reaction is favorable. And here are the four things we're going to discuss. Formation of a solid, right? This is called precipitation. Right? We can also form water. The specific formation of water reactions we're going to talk about here are acid-base reactions. Turns out there's many different types of reactions that produce water that aren't acid-base reactions, and the probably the most important one that you'll run into later is called condensation. This type of general reaction is very important in protein and peptide synthesis, forms peptide bonds. Next, we have transfer of electrons, right? And there's many different ways electrons can be transferred too, as we'll see when we classify reactions through one of these four main classifications. There's going to be sub-classifications. So this can be something kind of as general as a redox reaction, oxidation reduction. That's what transfer of electrons is called in a chemical sense. It can also mean that we have fire. It could also mean that we have electricity, and so on, right? So electron transfer reactions are a large class of reactions that usually provide a lot of vigorous reactions. The fourth kind we're going to look at is the formation of a gas. So this might be, we see some bubbles coming up. It's easy to mistake this, right? So this is not necessarily the same thing as when you have a glass of carbonated water, say, and you put it in a glass and you see bubbles come out. That's not quite the same thing, right? Because you know, you don't want your drink to have a chemical reaction going on when you drink it. This is something more physical. We'll talk about it a little bit, but it's similar, right? And it's important to realize that these four classes may occur together in whole or part. What that means is that you often could have an acid-base reaction that produces gas, right? You could have a precipitation reaction that's also an acid-base reaction. So these different classifications are not exclusive, right? They can happen together. Sometimes these are called exchange reactions, right? Exchange might be ions or parts of molecules. So that's what the exchange means. We're exchanging ions or parts of molecules. Right, so that's this idea. So one kind of an exchange reaction is a precipitation reaction. I think when we start drawing these reactions out and showing how they're balanced and how they work, then you'll see how this can be an exchange reaction. Acid-base reactions, right? They're actually can be very similar to precipitation reactions. Could be a precipitation reaction too, right? So these things can get complicated. A redox reaction is often an exchange reaction too. Sometimes you can see them as exchange reactions, sometimes you can't. So let's talk about precipitation. What I'd like to do to start is I would like to show you a video from YouTube that shows the beauty of precipitation reactions up close. Notice the motion or lack of motion in some of these precipitations. So that video is from Beautiful Chemistry.net. It's one of my favorite websites or YouTube sites for. Now in that video, they wrote the precipitation, the product of this reaction, the solid, in boldface, and wrote it down. Let's just start using this picture here on the left from the slide for what this reaction is. This reaction is barium nitrate, BaNO3, plus potassium chromate, K2CrO4. So notice that in a precipitation reaction, we start with two solutions that come together, right? Each solution is what we would say is soluble. In other words, there's no solid or precipitate beforehand, right? In each solution individually, it may be colored, right? We don't want to confuse the existence of color with a precipitate, right? A precipitate is a solid in the solution, right? So we have these two solutions that may or may not be colored, no solid. We put them together and we get a solid. And in this case, the solid is barium chromate. We write the state S, and then the other species form, in a molecular sense, potassium nitrate. And in order to balance this, we needed two. So there's the balanced reactions. Many times in this type of reaction, you draw an arrow down like this, which is supposed to show it falling out of solution, right? This is the precipitate. Or in other words, the product of this reaction. Okay. All right, so we have to think a little bit about what happens when we have an ionic compound that is soluble or dissolves in solution. So ionic compounds, these do more than simply dissolve in water, right? Dissolving means disappearing, right? So let me give you two examples that turn out to be quite different. If you take some sugar, some simple table sugar, and put it in water and stir it enough, it'll disappear in solution, right? So sugar will go to sugar, and we would say it's AQ, it's dissolved, right? So each individual sugar molecule is broken apart from the solid form and floats around in the water all by itself, right? But sugar is not an ionic compound, right? If we take something like table salt, sodium chloride, and we put this in water, H2O, then what we get free ions, right? So this does more than dissolves. The sugar, or I'm sorry, a salt ionizes in water, right? So it breaks apart into its constituent ions, and those species now float around in solution individually. These charged species float around individually in water, right? So we have a word to describe the difference, and that is an electrolyte. An electrolyte dissolves in water to give ions, right? This is ionization. They ionize when we get them on, they turn into ions. There's a way to measure this both qualitatively and quantitatively. Qualitatively, we can set up this pretty simple device. We have a device like this at school, which I can't show you because we're not at school. And it's a pretty good demonstration. All you do is you hook up a light bulb between a battery and two plates in a solution and do this in pure water. Turns out if you do this in pure water, the light bulb will not light up. This seems pretty weird, right? Because we're conditioned to think that you have the possibility of being electrocuted. For example, if you stand in a puddle of water in front of a electrical panel, right? And you touch the electrical panel. And it turns out that if you have pure water, you're pretty much safe for the most part, because pure water will not conduct electricity. In order to conduct electricity, you need ions. So the way this works, right, is if you have electrons, which are electricity, and they move through a wire like this, if the wire encounters water and we want to complete a circuit, like this. Well, in order to complete a circuit through water, we need ions to carry the charge. So we might have something like chloride carries the charge across, and then electrons can pick it up. This is an oversimplification, but basically ions are needed to carry charge through water. Okay, and so if we have some ions in solution, the light bulb will light up, right? And additionally, the kind of the strength of the light, or how bright the light is proportional to the number of ions, right? So if you just put like a couple grains of table salt in that water, the light would light up weakly. And if you put maybe a teaspoon or more in, it would be brighter. This is still fairly qualitative with this light bulb setup. It's not very sensitive to the concentration, but it is proportional to the concentration, right? So I do have another video for you to watch since I can't do the demo for you. Okay, I have to say that this demonstration is from Harvard University, so it's kind of boring and stuffy, but it's the best one I could find, so I apologize in advance.
Oh, hi. Today we're going to learn about solutions and how they conduct electricity, or don't. Tap water. Distilled water. Huh? What? Salt water, 1 teaspoon per cup. Hydrochloric acid. Nice. Sodium hydroxide. Just as concentrated. Sugar water. Sweet. Vinegar, a weak acid. Ethanol, a dissociative that doesn't dissociate. Don't try this at home. Barium sulfate. It's insoluble. No conductivity here.
So that was kind of trippy, wasn't it? It's kind of it's kind of funny. So there were some terms that Daniel, I'm assuming that was Daniel, that Daniel talked about here. I made a little table of the result of his demonstration, and he used some terms here. And what I'm going to say here is that what I'm writing down here is the strength of the bulb, right? How strong or how bright the bulb was, the strength of the bulb. And he used these terms too. You might have heard him mention weak and strong and so on, or even non-electrolyte. It turns out that there are degrees of electrolyte strength. And it turns out to depends upon amount of ionization. Okay, so if you think about it, we could have 0% ionization and 100% ionization, right? And an example of this is if you took sugar, right? We know that sugar can't ionize. So when we put it in water, it's 0% ionization, right? But that's because of the nature of sugar. As the semester goes on, we're going to find out a little bit more about these types of compounds and the forces and so on, and we'll understand it more and more. But because sugar can't ionize, its percent ionization is necessarily zero. But what about something like the example we know gave a very kind of strong light bulb, HCl? Well, it turns out that HCl, if we drew a kind of schematic reaction about what happens, here's HClAQ. We know that it's an acid, right? But an acid is kind of a subclass of ionic compounds where the positive ion, the metal ion, is a proton, okay? We know that this has the possibility of ionizing, right? And the light bulb test implied that the amount of ionization was quite high, right? So the idea is, which side of this reaction do we sit on? And it turns out that HCl in water goes to the right 100%, 100%. It's 100% ionized. So it turns out that that sits over there, right? And so when we take this this kind of description of how much ionization is proportional to how much brightness and light bulb we see, we could write down the other things too. We could put NaCl here, over here. We could put NaOH here, right? Now, what about vinegar and tap water, which were weak? Notice he had tap water and he had pure water, in other words, distilled water. So tap water is purified, but it turns out there's other things in tap water. My tap water is not very pure at all because I have a well. So there's all kinds of minerals and ions in there. And the more ions in the water, the more it'll register with the light bulb being bright. So it turns out that the tap water and the vinegar are in here somewhere in the middle. So we can say that because of the brightness from the light bulb that we saw, they're not 0% ionized, there's some ionization, but it's not 100% ionized like these other compounds. It turns out that we have some words for this, some descriptive words for this. A strong electrolyte is identically 100% ionized, right? A weak electrolyte is more than zero, but less than 100% ionized, right? It could be 85% ionized, and that's classified as a weak electrolyte. That's a little strange, but that's the definition, right? A non-electrolyte is 0% ionized, right? So I know you've heard this term electrolyte before, whether it's from Gatorade or another sports drink or so on, or maybe from Pedialyte or whatever, right? These are things that are full of electrolytes. That's just a fancy way of saying it's full of ions, right? And ions that are free in solution, not together as a precipitate. So now with this description, we're ready to talk a little bit more about precipitation. So let's go back and look at our slide over here of our barium nitrate and potassium chromate reaction. Now I did go ahead and write the results of this reaction that we know, but let's go back and kind of start over. Each solution can be visualized as a bunch of free ions, right? And they colored the left-hand potassium chromate one a little bit yellow because that's the way the solution looks, right? It's yellow, but it's clear. But barium nitrate is a clear solution, right? And the numbers and types of ions are all correct here. 2 nitrates for each barium and 2 potassiums for each chromate. So what happens before we mix them looks like this picture, right? So as I mentioned before, a precipitation reaction is an example of an exchange reaction. And what happens is the ions kind of do a square dance thing and change partners, right? So the possible products come from the partners changing. So the way you write this is you write K2CrO4 AQ, right? We did this before. BaNO3 2AQ. Sometimes students ask me, does it matter which one occurs first? And it totally doesn't, right? You'll notice that a few minutes ago, I wrote the exact same reactant species the other way around. So now what we do is we write down the possible products, right? We pretend that we don't know that what the product is, right? And in the reactant case, we have potassium with chromate. So we're going to put the potassium with the nitrate and make sure that it's balanced for charge, right? And then we're going to put the barium with the chromate. And finally, we're going to make sure this is balanced. So what we're going to do here is generally, we're going to say, well, I'm not sure what the product is. The product, the precipitate, could either be potassium nitrate or barium chromate, right? One of these two is a possible precipitate. So we call these the possible products. Okay. So the next thing we have to do is we have to decide what products are formed, right? And that's really what we've done here, right? We've said, okay, well, really what happens at first is all the ions are in solution together, right? And we know that the product cannot be potassium chromate because that's what we started with in one solution. We know the products can't be barium nitrate because that's what started in the other solution. So the possible products are either potassium nitrate or barium chromate. This is just another way in kind of a tabular form to write down what I did in a chemical equation, right? So what we need to do now is we need to either do some more experiments or we need some more information. If we know that potassium nitrate on the shelf, right? If we go to our stockroom and ask the stockroom person, hey, what color is potassium nitrate, right? It turns out to be a white solid. And we say, hey, what color is barium chromate? This turns out to be a yellow solid. We can kind of compare this, right? We can kind of compare this with what we see in the solution, which turns out to be a yellow solid. And that can tell us that our product is barium chromate, right? So that might be how we experimentally decide that the product, right, is barium chromate, right? And we can draw an arrow here. The other species are potassium nitrate. And now let me fill in K2CrO4 was one reactant, and barium nitrate was the other reactant. So what we've done here is kind of experimental, at least here in our heads, we've determined that the product is barium chromate. Okay, well, it turns out that these experiments have been done, of course. And what these experiments have allowed us to do is to determine a set of general solubility rules. It turns out that one of the things that you find out if you do a bunch of these precipitation experiments is that sulfide salts tend to be insoluble. In other words, either by starting with a sulfide salt and putting it in water and trying to dissolve it, we find it doesn't dissolve. Or you take a sulfide salt that you know is soluble, like sodium sulfide, smelly, but soluble, right? And you mix it with lead chloride, which is also soluble, and you mix them together, and you find out that the product, through trial and error and through some deductive reasoning, that the lead sulfide is the precipitate. And over and over and over again, we find out, for example, that sulfide salts tend to be insoluble, right? And potassium salts tend to be soluble. And we gather all this information, and what we get are the solubility rules, right? Over here on this slide, right? And we can use these solubility rules to predict products when we mix two soluble solutions together. There's some things to know about these solubility rules. These rules are hierarchical. That means that rule 1 takes precedence over rule 2, and so on. Rule 2 is more important than rule 5, and so on. So if we go through our tests and we kind of find a conflict between two rules, the lower numbered rule, the higher placed rule wins. Right, so that's how that works. So the question is, how do we use solubility rules? Well, typically we just have a potential precipitation reaction, and we have to determine what the products are. So it's kind of two things. It's, first of all, we have to figure out what the possible products are, and then we have to decide not only which product forms, but whether a product forms, right? And the solubility rules will tell us that. So let's do a real simple example, right? Typically what you have is you have something like a problem that will say you mix hydrosulfuric acid, right, plus nickel 2 sulfate, right, and identify, it'll say identify what solid forms if no solid forms, or no solid is expected to form, right? What we usually do if no solid forms, we write NR for no reaction as a product, right? All right, so the first step is we write down the exchange products, right? In other words, we're gonna switch the partners and see what we get. So there's my reaction arrow. Now I'm just concerned about the right side. Let me center myself a little better here. We're just concerned with the right side of the reaction. I'm going to put the hydrogen with the sulfate. Sulfate is 2-, so I need to put 2 hydrogens to make it complete. This is, of course, this is, of course, sulfuric acid. And then I'm going to put the nickel 2 with the sulfide, right? So those are my 2 possible products. And remember, I call them possible products because they're only considered a product if we get a precipitate, right? We'll investigate this a little further in a few minutes. Okay, so we write down the exchange products. And then we look at the rules to decide what product, if any, is formed, right? So we're just going to go down the solubility rules. Most nitrate salts are soluble. Well, there's no nitrates here. Most salts of sodium, potassium, and ammonium are soluble. Don't have any of those either. Most chloride salts are soluble. Here's some exceptions. Don't have any chloride salts. Most sulfate salts are soluble. Notable exceptions are, okay, so this is a sulfate salt, but I should also say that acids are soluble. This is kind of an important rule in this case, because remember I said we could have a combination of an acid-base reaction and a precipitation. This is not exactly an acid-base reaction, okay? But we should add this to our rules. This might be considered rule 0. Acids are soluble, okay? So what that tells us, right, is that H2SO4 is AQ. This does not tell us necessarily that nickel sulfide is insoluble or precipitates. We need a separate rule for that. Rule 5 says most hydroxide compounds are only slightly soluble. And for the purposes of teaching, I like to get rid of the fuzzy words like slightly or partially or mostly, right? So I turn slightly into in. In other words, hydroxide compounds are insoluble. And the exceptions come from rule 2. In other words, if you have potassium hydroxide or sodium hydroxide, these guys are soluble because rule 2 deals with potassium and sodium salts. Sulfide carbonates and phosphates are only slightly soluble. Again, I would cross out the only slightly and write in, right? In other words, a sulfide salt is insoluble or forms a precipitate. Here we have a sulfide salt. And again, I like to draw the arrow to emphasize that. So nickel sulfide would be considered a product here. Okay, let's do another example. We mix some sodium nitrate plus potassium chloride, right? First step is exchange the partners and see what we get. We get sodium chloride plus potassium nitrate. And then we're going to test the products, right? We shouldn't have to test the reactants because if the reactants were not soluble, we wouldn't have a problem to begin with, right? So we can safely assume the reactants are soluble. All right, so let's go down our list. Well, rule 1 says nitrate salts are soluble. Well, okay, we write AQ for potassium nitrate. Rule 2 says most salts of sodium are soluble. Well, so here we get a case where what we would write, well, there's no precipitate, no product. So what would we write? We would write NaNO3 AQ plus KCl AQ, no reaction. That's our answer, NR, like that. Okay, writes it clearly. This little box chart is supposed to show the solubility rules in a more visual manner, right? And here's another one, right? This is more complete, right? And it's worth it to kind of go through and see what each rule really specifies, right? So this is like a longer version of the solubility rules, but the other one is more a working version. Let's think about the way these reactions really occur, or what happens when we describe these reactions, because the ions floating around the solution, sometimes they're free and sometimes they're loose. So let's think about what this means. Identifying species in aqueous solution. This is really section 7.3 in your book. Okay. Well, let's take one of our soluble compounds like sodium nitrate. Sodium nitrate. When we write NaNO3AQ, what does this mean? In water, this really means Na plus AQ plus NO3 minus AQ, right? That's what it means. So even though we write this soluble salt in a molecular way, we really only write it in a molecular way so it's convenient. It's more convenient to write and describe, but we have to know, we have to realize that it's two free ions, right? So the NaNO3 is really molecular shorthand, right? Okay. It's easier to write. But what this means is we can see now a little bit better what no reaction means. So let's go back, right? Let's go back and write this reaction here in a full manner, right? So what we had was NaNO3AQ plus KCl AQ. I'm going to cram this in here really small, right? And the swapping gave us KNO3AQ plus NaClAQ, right? We would call this a molecular equation, right? So most of the equations we've been writing so far are molecular equations because it's just easier to write things in a neutral, an electrically neutral molecular way, right? Because if we don't, if we write what really happens, but really, here's a better representation, right? What really happens is the sodium ion is free to swim around and the nitrate ion is free to swim around and the potassium ion is free to swim around and chloride ion, you get the idea, right? And then on the other side, right, if I just take the same order as I've written it down, I have the potassium ion, and then I have the nitrate ion, and then I have the sodium ion, and I have the chloride ion. So now think about algebra, right? I'm sorry to do this to you, but it's convenient to think about this in an algebraic sense, right? In algebraic sense, if I identify the sodium as A and the nitrate as B and the potassium as C and the chloride as D, right? And we have the reaction arrow, which is the same really as an equality sign in math, right? Then what I have is the potassium, which was C, and the nitrate, which was B, and the sodium, which was A, and the chloride, which was D. Now, one of the most basic things you learn in algebra when you're learning about properties, right? And I have to tell you, I don't remember the name of this property because I'm a chemist, not a mathematician. But basically it means it doesn't matter what order you add things, right? So A plus B plus C plus D is the same as C plus B plus A plus D. And this is saying the left-hand side equals right-hand side. This is no change. Hence, no reaction. All we've done is mix things up. We haven't really produced anything, right? So this is why we would say no reaction. When we write an equation in this way, we call this a full ionic equation, right? A full ionic equation shows all separated ions. But this is kind of a pain, right? I mean, it seems like a lot of work. You have to worry about the charges and have to put twice as many AQs down and everything. So it's a lot more writing work than writing a molecular equation, right? Let me catch up here on the slides. I'm actually going to come back and talk about this as kind of a review to break things up a little bit, okay? All right, now there's one more type of equation that we can write when we're dealing with ions, right? And this is called a net ionic equation. A net ionic equation shows only the species that are directly involved. Well, we can't use the immediately previous reaction to illustrate what a net ionic equation is because there's no reaction. But what we can do, right, is we can go all the way back up here and we can use our H2S plus nickel sulfide reaction. I'm sorry, nickel sulfate reaction, right? So let's do that again. H2S plus NiSO4 goes to, let's write the result. We already know the result of this reaction, right? It's NiS, I'm going to put the product first, plus H2SO4AQ. Well, there's two ways we can figure out what the net ionic equation is. One way is to look at both sides of the equation, find everything that's AQ and separate it, and then eliminate things that are on both sides, right? That's one way. There's an easier way. The easiest way to get the net ionic equation is to start with the product, right? We have the whole equation written out here, but what I'm going to do is I'm just going to write the product, nickel sulfide solid, right? And then what we're going to do is work backwards. Nickel sulfide is composed of nickel 2, right? I should have said nickel 2 sulfide. So there's the net ionic equation, right? It's easier to start with the product and break the product up than go the other way and eliminate things, right? Typically in a problem, you'll be given a precipitation reaction or potential precipitation reaction, and you'll be asked to write the molecular equation, the full ionic equation, and the net ionic equation, okay? Okay, let's take a few minutes just to do a little bit of a review using the slides that we provide for you. First of all, let's look at this concept check. Which of the following ions form compounds with lead that are generally soluble in water? So you can do this along with the solubility rules if you would like, or you can try to test yourself by what you know so far. And you'll start to see patterns here. For example, chloride salts and nitrate salts are generally soluble, and sulfides are generally insoluble, and sulfates are kind of in between. There are exceptions for sulfates, for example. There's a couple exceptions for chloride too. Right, so let's see what we can come up with. So I'm gonna guess and say that sulfides are generally insoluble, right? Chlorides are generally soluble in water, right? Chlorides are generally soluble in water. Nitrates are generally soluble in water. Sulfates are usually soluble in water. And sodium salts are, well, in this case, sodium is not applicable because sodium will not form a salt with another positive ion, right? So this is kind of a red herring they threw in here to see if you're paying attention. Now, let's go back and think about the solubility rules a little bit, right? Because chloride salts are soluble, chloride salts are soluble, but there are some exceptions. And if you look at the solubility rules, the exceptions include lead too. So by paying close attention to the solubility rules, we find out that PbCl2 is insoluble, right? Nitrate salts, they don't really have any exceptions, so I think that's a good choice. Sulfate salts are generally soluble, but again, there's an exception, or there are exceptions that include lead sulfate. It turns out before when I mentioned that sulfide salts tend to be insoluble, that's kind of from the anion side. If you look from the cation side, then what you'll find is that lead is very often insoluble when many of its other metallic brethren are soluble. So what we're left with is only nitrate as the soluble salt that fits here. Right? Let's look at this concept check, right? It says a sodium phosphate solution, sodium phosphate, Na3PO4, reacts with a lead 2 nitrate solution. So this is pretty good practice for writing these things down. What precipitate, if any, will form? Well, first of all, we want to swap the ionic partners and see what our possible products are, NaNO3. And in this case, I'm not going to worry about balancing the equation because I just want to know what's formed. The other possible product would be lead 2 phosphate. And you have to be careful with this, right? That's the possible product. All right. Let's look and see if we can eliminate some of these questions just by knowing what the possible products are, right? And some other things. Well, by now, maybe you know that sodium salts and nitrate salts are usually soluble, especially with each other. So we know sodium nitrate's not going to be a possible precipitate. We know that lead nitrate, lead 2 nitrate, is not going to be a precipitate because we started with that, right? And if we started with that, it is almost by definition, it's going to be soluble. Well, our choices here are no precipitate or lead 2 phosphate. And it turns out that phosphate salts are usually insoluble, right? So phosphate salts are usually insoluble, and you'll also find that lead salts are usually insoluble, right? They're usually listed as exceptions for the more soluble salts. So I'm going to guess the answer is lead phosphate. And that turns out to be true. Okay, here's another review question. Consider a solution with nitrate. I'm just going to write these down over here. Lead 2, potassium, silver ion, chloride, sulfate, and phosphate. When all are allowed to react, and there's plenty available of each, how many different solids will form? Well, you have to go through the solubility rules. So let me now that I've had this written down, let me slide back to the solubility rules and see what we can form. And we'll take each one in turn. Really, the more organized way to do this would be to do it this way. Lead to potassium and silver, nitrate, chloride, sulfate, and phosphate. Do something like this, right? And so, for example, lead, if I go here to this space, lead and nitrate form lead nitrate, but nitrate salts are soluble, right? So I'm going to leave that as an empty box, okay? Lead and chloride, right? We see that lead chloride is an exception to the chloride solubility rules. So I'm going to mark that with an X. Lead chloride, lead 2 chloride is a product. Lead sulfate, right? Lead sulfate's exception, and so on. So you could fill out a chart like this, right? And it's not surprising to find that lead is insoluble with many of these things. Potassium salts are soluble, so I'm going to leave that blank, right? Potassium salts are soluble. Silver is another exception with chloride, right? It's not an exception with sulfate, though. But the way the solubility rules are written is it basically says phosphate salts are insoluble, and it doesn't really give any exceptions, right? So we would have this kind of result where the X's denote a product. So let me skip back ahead to where we were. This says 5 different solids. Let's see if we're right. Lead chloride, lead 2 chloride, lead 2 sulfate, lead 2 phosphate, silver chloride, silver phosphate. Good. Okay. So here's a review of our molecular equations, complete ionic equations, net ionic equations. Okay. So let's practice one of those too. Let's write Na2SO4, sodium sulfate, plus lead 2 nitrate. Right? So let's first write the molecular equation, right? This is my favorite out of the 3 because it involves the least amount of writing. We start with the sodium sulfate, AQ, the lead nitrate, AQ. Swap the partners, right? We're going to get lead sulfate and 2 sodium nitrates. We check the solubility rules and we'll find lead sulfate is the precipitate. So there's the molecular equation. Now let's write the full ionic equation. The full ionic equation, remember, splits everything as ions. So first we have 2 sodium ions plus sulfate ion plus lead ion, lead 2 ion plus 2 nitrate ions. Right? And on the other side, we have the lead 2 sulfate plus 2 sodium ions plus 2 nitrate ions. Right? That's the full ionic equation. The net ionic equation. Now, when I did this the first time, I took the product and worked backwards. Let's go the other way. And what I'm going to use is the full ionic equation to go the other way to eliminate things that are on both sides, right? If we do that, we can see that we have sodium existing on both sides. We have nitrate existing on both sides. And what we're left with is the sulfate and the lead going to lead 2 sulfate. Now, if we wrote this just exactly the order that it occurs, we would get sulfate ion plus lead ion goes to lead 2, making a little bit of a sloppy mistake here, lead 2 sulfate, right? And again, this illustrates the fact that it doesn't matter the order of the ions you write down. I would say generally most chemists write the metal ion, the positive ion first, and the negative ion second. This is kind of because chemists tend to have a metal-centric or positive ion-centric view of things. I don't know why it's that way. That's just usually the way it is, but it really doesn't matter. Okay, now let's move on to section 7.4. Acid-base reactions. It turns out that there's many chemical definitions of what an acid is and what a base is. And what we're going to do is we're going to use a common definition of acids and bases, and that's the Arrhenius definition. Svante Arrhenius, as well as having one of the most interesting names in chemistry, actually did a lot of different things in chemistry. Did some kinetics and other physical chemistry, but I think probably what he's most famous for is the Arrhenius definition of an acid and a base, right? So according to the Arrhenius definition, an acid will produce aqueous hydrogen ions in water. Right? A base produces aqueous hydroxide ions in water. This is actually a more general definition than it sounds, because you notice it doesn't say that an acid contains H plus or a base contains H plus. It says the net result of the reaction of this stuff when you put it in water is either protons or hydroxide. So very briefly, that means that we could have an acid and we put this in water, and at least one result is this, right? And we could have a base and we put this in water, and at least one result, we might get other things too, but we at least get hydroxide ion. Now, without going into too much detail now, what we're going to find is that there are species that don't contain H plus and don't contain OH that fit these definitions, right? And that's what makes this definition of an acid and a base so useful and so flexible. For the most part, our acids that we see here H plus and anion, right? This is kind of how we define them when we did nomenclature. And bases are a metal plus OH, right? So an example of the first one would be HCl, HC2H3O2, and H2SO4. An example of this base definition would be KOH, NaOH, and even BaOH too. Okay, we're going to further concern ourselves mostly with strong acids and bases. So one of the things that is a big misconception in chemistry is that the term strong acid means the same thing as reactive or destructive or dangerous. Generally, all acids are can be pretty dangerous, but the word strong has to do with strong electrolyte. So the strong or weak in strong or weak acid or base refers directly to a strong or weak electrolyte. In other words, does it ionize 100% or less than 100%? Okay. So then the question becomes, how do you tell a strong acid from a weak acid? Well, it turns out this is not too hard. There are only a few strong acids. HCl, HI, H2SO4, HClO4, and I know I'm forgetting one too, HNO3. These are generally accepted as the 5 strong acids. There are, probably some more that aren't so common, but if you memorize these 5 acids as being strong, you could mostly safely say every other acid is weak. Now, bases are a little bit more complicated because it's more common for the flexibility of the Arrhenius definition to fit a base than an acid. But for now, we can say strong bases are KOH, NaOH, LiOH, right? And that's good enough for now. That'll do for now. Okay. So here's on the slide, here's a schematic of 3 of the common strong acids and what happens when you put them into water, right? This is strong in the sense of 100% ionization, and it's just like a 100% soluble salt, but in this case, the positive part of the salt comes from a proton, okay? And I've mentioned this in my classes many times before too, but hydrogen chloride is kind of funny because hydrogen chloride, if it's not in water, it's actually usually a gas, right? And then we would call it hydrogen chloride. Let me write that down. But if it's aqueous, it's hydrochloric acid. So technically, if the state is not attached to species such as this, then it's hard to figure out which it is. I would say usually if we just write HCl, we mean aqueous HCl. And that's a relatively safe assumption to make. All right, so here's some examples of the bases, KOH and NaOH, and they do a very similar thing with their respective ions, right? But in this case, the emphasis is on the hydroxide. Now, what's interesting is what happens when we put them together. An acid, let me try this again. An acid plus a base yields water and a salt. So let's see how this happens. Let's do the most common acid-base reaction that people know of, HCl plus NaOH, the most common acid and the most common base. Well, the H and the OH go together and they form the water, right? So the formation of liquid water is a signature of an acid-base reaction. And then the other two ions get together, at least in a molecular sense, right? But of course, we know the full ionic equation would look like this: H plus Cl minus plus Na plus OH minus yields H2O plus Na plus Cl minus. So what this means is it gives us the net ionic equation, H plus OH to water. In other words, whoops. H plus OH minus gives us H2O is generally the net ionic equation for an acid-base reaction. I say generally because once in a while you run into the salt that's formed as being insoluble. And in that case, you have kind of both a precipitation and an acid-base reaction. Not super common, but it is possible. So if you ever see that happening, or you think it might be happening, then maybe it does. If you form an insoluble salt, then that's exactly what can happen, right? So this was really a very brief introduction to reactions of acids and bases. We're going to do things later when we actually work with stoichiometry. We'll do things like acid-base titrations and talk about indicators and so on. It becomes a little bit more interesting. But for now, we're just going to try to identify the reactions and find some characteristics. By the way, another product of this reaction is heat. For example, if you mix an acid and a base together, it gets warm. And maybe you've heard that you're supposed to add, if you're diluting an acid, for example, you should add the acid to the water, not the other way around. That's because a lot of heat is generated when these compounds, both acid and base compounds, dilute or react with each other. And that heat, when you add the water to the acid, can be uncontrolled and it can spit the solution back up into your face and be very dangerous. Okay. This kind of reaction is also called a neutralization reaction, right? And that has to do with the fact that if we're not acid rich or we're not base rich in water, we're neutral. We're neither acid or base, we're neutral. And if this reaction is exactly equal, then we call it a neutralization. Okay. So let's take a second to look at this concept check. What is the net ionic equation for the reaction of nitric acid and lithium hydroxide? Well, here, if you remember that the net ionic equation for any acid-base reaction is H plus OH is H2O. All we have to do is look for that. Here it is. That's got to be the net ionic equation, right? Okay. Next, we have a qualitative description of oxidation, reduction, reactions. These are also known as redox. It's just one of those things we say oxidation reduction, but if we, you know how we love to make shorter words out of everything, ox-red sounds dumber than redox, but we don't say reduction oxidation reactions. It's just one of those things that's kind of funny, isn't it? This is transfer of electrons, right? We have a transfer of electrons from one species to another. Here's the example, 2 Mg plus O2 gas goes to 2 MgO. And you have to dissect this ionic compound on the product side to see what's happening. We have Mg2 and O2 minus, right? So the oxygen is going from neutral, O2 is neutral, right, to a 2 minus oxygen. And the magnesium is going from a neutral, again, to a 2 plus. Let's write this out a little bit more kind of in a two-part way. What we have for each magnesium, right, is this forms a magnesium ion. Well, what's hidden here are the electrons themselves. If we balance this reaction with charge with electrons, then we end up with 2 electrons, right? So 2 electrons are coming off the magnesium, each magnesium atom. And then let's see what happens with the oxygen. The oxygen is going to form oxides. In this case, since we start with O2, we have to be careful to give ourselves 2 oxides. That's a total of 4 minus charge on the right. And we balance these little mini reactions. We call these half reactions. We balance these half reactions with electrons only, right? So if we have 4 minus on the right, we need to have 4 minus on the left, and we accomplish this with 4 electrons, right? Now we can see from our overall reaction that we have 2 magnesiums, right? 2 magnesiums for every oxygen molecule, right? And we can see that the way this balances is 4 electrons to 4 electrons. So one of the things I tell my students when you first balance chemical equations is we don't really balance too many oxidation reduction reactions by inspection. And that's essentially the way we're balancing right now. We call this by inspection. The implication is it's not too difficult. But oxidation reduction reactions in general can be very complicated. They often involve water or other things, and you just have to try to figure out how that is. And it turns out there's kind of a methodical system to do this. We're not going to learn this right now, but one very important part of this system is that the electrons have to balance, right? Electrons are never left over, right? And this actually determines the stoichiometry. So the reason why there's 2 magnesiums for every oxygen molecule is that the oxygen molecule half reaction has 4 electrons. Each magnesium half reaction has 2 electrons. So in order for the electrons to balance, we need this one twice. Right? Does that make sense? That gives the overall reactions. That's really, in a nutshell, how you balance these complicated oxidation reduction reactions. But as I said, you're not really going to be responsible for figuring out how this works right now. Right? So let's think about what's happening here. Let me go back here. Let's think about what's happening in this reaction on the slide. The reaction on the slide says, if you look at it, we have 2 aluminums. I'm going to leave the states off, right? And then we have Fe2O3, that's iron 3 oxide, goes to 2 Fe plus Al2O3. So again, this can be seen as an exchange reaction. The oxygen's basically giving up the irons and taking in the aluminums, right? So let's think about what's happening here. Here, the aluminum is in a compound and it's 3 plus. Here, the iron is in a compound and it's 3 plus. And if we kind of write this schematically, we can see what's happening, right? The aluminum is going to aluminum 3 plus, In order to do that, each aluminum loses 3 electrons. The iron 3 is going to iron neutral, and to do that we need to add 3 electrons, right? So if we can draw this cartoon, now we can come over here and see what's happening and see which one of these answers is right. Aluminum gains 3 electrons. Well, right, we know aluminum is losing electrons. And we know that iron 3 is gaining electrons. So let's look for iron gaining and aluminum losing. So we have to throw out A and B because we know aluminum doesn't gain. Aluminum does lose though, so it's got to be either C or D. We've said that iron gains electrons. Remember, we have to balance charge with electrons. So iron's gaining electrons, and it's the iron that's gaining, not the oxygen. So it looks like the answer is going to be D. Okay. Well, usually what happens in an oxidation reduction reaction, a metal, not a metal ion, a metal, right? So let's write metal solid loses electrons, or a metal ion gains electrons. A non-metal will gain electrons. This is generally what happens, right? Let me write my magnesium reaction again, my magnesium oxide reaction again. Remember, we had magnesium going to magnesium ion plus 2 electrons. We had oxygen plus 4 electrons going to 2 oxides, right? Where does the name oxidation reduction come from? It turns out reduction means reduction in charge. So maybe you've seen reduction is loss. Well, that's not exactly right because I just said that something else. So I'm going to give myself a second to reset. Okay, how can we relate these two equations to the words oxidation and reduction? It turns out that reduction refers to the reduction in charge. And that's where this all starts. So what we want to do here is we want to see which of these two species is going down in charge. Magnesium is going from magnesium neutral to +2. So magnesium's gaining its charge. So that must mean the oxygen is the reduction, right? So we can see this, that each oxygen is going from neutral to oxide 2 minus. So this is a reduction in charge. But what this really means is that it's a gain of electrons. Right? So maybe you've seen this, reduction is gain. Reduction is gain. Well, this is half of the mnemonic oil rig. What's the other half? Oxidation is loss of electrons. And we can see that up from this magnesium half reaction, right? Magnesium coughs up 2 electrons, right? Like a bad habit. And that's oxidation is loss. Oxidation is loss. And usually, right, I did this backwards, but that's where the oil rig mnemonic comes from. The other one is Leo Ger. I don't know how much this is used anymore, but loss of electrons, oxidation, gain of electrons, reduction. So maybe those two things can help you. We don't really specify that too much in this class. We don't test you too much on that class, in this class, but it is there. And if you can learn it now, it will help you later. Okay, so now we've kind of come full circle. We started talking about driving forces, and I mentioned very briefly at the beginning of lecture about ways to classify a reaction in terms of the driving forces, right? And we're going to try to classify our reactions that we see through these main methods, right? So we have the main ways to classify. Precipitation, that's formation of a solid. Acid base, that's formation of water, acid base reactions. Transfer of electrons is a redox or oxidation reduction reaction. Formation of a gas, this is usually within other classifications. In other words, formation of a gas is usually not its own classification, and we'll give some examples of this. And we might also say, in some cases, it's a net formation of a gas. In other words, you end up with more gas than you start with. Okay. Okay. Now, here's our precipitation reaction, right? Here's another way to look at it. We talked earlier about these being a form of an exchange reaction. This is also called a double displacement reaction, right? In other words, we're doing two partner switches, right? Now, it's hard to have one partner switch in this type of reaction without another, so it's necessary, but you'll see why it's called double displacement in a minute or two, I think, right? This is a precipitation reaction. Usually these are pretty evident, right? Now remember I said sometimes more than one classification can happen together. An acid-base reaction, remember we want to look for the formation of water, right? And a salt. Once in a while, something else will happen. Once in a while, there'll be some gas formed. Once in a while, there will also be a precipitate formed, right? So in an acid-base reaction, most of the time, we just want to look for the formation of water and at least one acid or base on the other side. I think most of the time, for us in this class, we're going to be able to easily identify both the acid and the base on the reactant side of the equation. Oxidation reduction reactions are very interesting. Now I'm completely aware that when a professor says something is interesting, that usually means to a student hard, right? But let's look at some helpful things, some tips or tricks, and also some classifications. Well, in an oxidation reduction reaction, you often have an element on one side of the reaction, and that element becomes a combined form, right? So let's look at this first example on the slide. We have two elements, right? Lithium and fluoride, and they combine with each other to form lithium fluoride. So anytime you have a neutral, charge neutral elemental form that becomes combined, it's going to be an oxidation reduction reaction, right? This second example, again, iron, metallic iron, which is neutral. And over here we have combined iron, right? Combined iron, which is necessarily a charged species, a metallic +2 ion. Notice what else we form here hydrogen gas. So very often in an oxidation reduction reaction, you will form a gas such as hydrogen or chlorine or oxygen, because this is the species that's either going to take electrons or give up electrons, becoming itself an elemental species, right? So you see for many of these reactions, we have an elemental species on one side and a combined form of that element on the other side. So that is one way to identify an oxidation reduction reaction, right? So here's an example of an oxidation reduction reaction that forms a gas. Very typically, we'll take a reactive metal or a soft metal and dissolve it in something like HCl. And the chloride part of the HCl forms a salt with the metal ion that's formed. But the hydrogen ions take up an electron. Remember, hydrogen ions are H+. Each hydrogen ion will take one electron, combine with another hydrogen ion, and it's one electron to form H2. So this is an oxidation reduction reaction. That's also a gas formation reaction. It's also a single replacement reaction, right? So in a way, what we've got here is the zinc, which we could call A, and we've got the HCl, BC, and the zinc's going to come in here and it's going to knock off the hydrogen and it's going to leave the AC plus B2. Single displacement reaction, right? Single displacement reaction. And in order to do this, of course, we have to do something like this. But you get the idea. A single displacement reaction is not two pairs of things. It's one thing plus a pair. The one thing comes in and knocks the other one off, right? Kind of a violent way to think about it, but that's a single displacement reaction. So gas formation is another signature of redox. Okay. Combustion. What is combustion? Often you hear a verbal description of a reaction as something like propane burns in air to form carbon dioxide and water. Well, the burns in air thing really says reaction with oxygen, right? Burning. Air has a lot of oxygen in it, has essentially an infinite supply of oxygen, right? So that's the burns in air really means reacts with oxygen. And this is combustion. So combustions are redox reactions. So here's a combustion, a simple combustion. Propane, such as the propane in a grill. This is a balanced reaction. Right? Well, how do I know it's a redox reaction? Well, look, I have elemental oxygen on the left, combined oxygen on the right. This is one of my signatures. Look for an element on one side. So what you'll find out is this qualifies as an oxidation reduction reaction. But this is an example of an oxidation reduction reaction that's a little bit more difficult to see the charge changes happening, right? So this element on one side combined on the other is a kind of quick and dirty way to imply that there's a charge change going on, right? So combustions are redox reactions. What is a combustion? Anything, if we have some stuff plus O2 gives products, this could be considered a combustion reaction. For example, we can burn S8 in oxygen, 8SO2. So it turns out that we need 8 O2s to react with the one S8. We can have NH3, we get NO2, two NO2s plus H2O. So oxides are the general product of combustions. There's another subclass of oxidation reactions, usually oxidation reactions we call synthesis. The general form of the synthesis reaction is A plus B going to one thing C, right? Synthesis reaction, two things coming into one. Okay, an example is a combustion, right? This is still a combustion, right? Carbon plus oxygen gives us CO2. That's really a combustion, but it could also be called a synthesis. So I know what you're thinking. How would I classify this reaction? I would say this reaction is first a redox reaction. That's a more general classification. It's also a combustion. It's also a synthesis, right? I would say in the real world, chemists are a little bit more particular about what they consider to be a synthesis, but this is the technical definition of a synthesis. What if we do the opposite? We get a decomposition. In other words, if we take one thing and break it down into simpler things, we talked about this a little bit when we talked about forming compounds or how to classify compounds versus elements. If you decompose a compound at its base form, you get elements, right? You don't always have to get elements from a decomposition, but that's just the simplest example, right? An example is H2O2, hydrogen peroxide, gives us 2H2O, if I do this right, plus O2. That's a decomposition reaction. And in this case, this decomposition reaction doesn't form just elements, it forms water compound too, right? So it doesn't have to be going all the way to the elemental form to qualify as a decomposition reaction. Okay. So here's the full kind of classification scheme. And you can see oxidation reduction is the most interesting, right? And the classifications don't necessarily stop there with oxidation reduction reactions, but they will for us here, okay? Well, here's a reaction. This looks a little bit familiar. It's not quite what I wrote down. How would I classify this reaction? Well, let's see here. We have elements going to a compound. So we could call this an oxidation reduction reaction. I've got two things, A plus B going to C, going to one thing. I could call this a synthesis reaction, right? I've got hydrogen and I'm burning it in air. In other words, reacting with oxygen. This is really what happened to the Hindenburg in 1936. It's also a combustion. So it turns out that this reaction could be classified as each of these. Again, remember the most general classification would be oxidation reduction, and synthesis and combustion would be below that. Okay, so that's the end of chapter 7. I hope the lecture was useful to you. If you have any questions about what you saw, you can ask me directly, or you can ask Dr. Zhao or Dr. Starr. I'm sure they'd be happy to help you. And look for more of those beautiful chemistry videos on YouTube sometime. They are really amazing, and the photography is just stunning.